Every glass of water you've ever had might contain molecules that were flying through space on a comet millions of years before Earth even existed. That's not poetry. That's what a space telescope actually proved in 2011. And the story of how we figured it out rewrites everything we thought we knew about where our planet's water came from, starting with a comet that nobody expected to matter, cometary water composition. In 2011, the Herschel Space Observatory pointed its instruments at a small comet called 103P/Hartley 2 and found something that shook planetary science to its core. The water vapor coming off that comet had a deuterium to hydrogen ratio that almost perfectly matched Earth's oceans. That might sound like a dry technical detail, but here's the thing. For decades, scientists had basically ruled out comets as the source of our water. Every comet we'd ever measured had the wrong isotopic signature. The ratios were off. Textbooks said so. Case closed. But Hartley 2 blew a hole in that consensus with a single measurement, and this wasn't some rough estimate either. Herschel was reading the comet's water output in real time, watching it shed 40 to 50 kilograms of water per second at closest approach. That's precision instrumentation catching a comet actively bleeding water into space, molecule by molecule. But here's where it gets complicated. Herschel also observed other comets, and their water compositions were completely different. The solar system's icy bodies aren't uniform at all. They're wildly chemically diverse, which means some comets could have delivered Earth's water while others had nothing to do with it. The deeper implication goes beyond water. If comets carry water to Earth, they may have also carried the organic compounds and chemical preconditions for life itself. You might literally owe your existence to a dirty snowball that crashed into a young planet billions of years ago, and that debate is still very much alive. But if the origin of Earth's water feels like a big discovery, wait until you hear about an entire solar system packed with potentially habitable worlds, all found by a single telescope. Exoplanet atmospheres. Before JWST launched, we had meaningfully characterized roughly 30 exoplanet atmospheres. 30. Across every telescope humanity had ever pointed at the sky. Since JWST started operating in 2022, the number has exploded past 5,000. That's not an incremental improvement. That's an entirely different science. And the very first demonstration of this power was WASP-96b, a hot Jupiter set in 1,150 light years away. JWST's first science image package in July 2022 included a full spectroscopic breakdown of this planet's atmosphere, detecting water vapor, methane, and carbon dioxide in more detail than all previous exoplanet observations combined. One image package, one planet, more data than decades of prior work. But here's where it gets genuinely unsettling. In September 2023, JWST turned its instruments toward K2-18b, a sub-Neptune 124 light-years from Earth, and buried in the atmospheric data was something nobody expected to find this soon: dimethyl sulfide, DMS. On Earth, that compound is produced almost exclusively by living organisms: phytoplankton, bacteria, biological processes. That's basically the only way we know it gets made. Now, before anyone starts printing "We found aliens" headlines, the science is more careful than that. Abiotic chemical processes that could theoretically produce DMS haven't been ruled out yet. This is not confirmation of life, but it is the first time a compound directly associated with biology has ever been detected in an exoplanet's atmosphere. That distinction matters enormously because the question shifted from "can we even detect biosignatures?" to "we just did." Now, what explains it? The reason JWST keeps finding things nobody else could is sensitivity. It can pick up atmospheric features as subtle as 20 parts per million in composition. Compounds that were completely invisible to every previous telescope are now showing up in routine observations. But if you think analyzing atmospheres is impressive, wait until you see what happens when JWST catches entire solar systems in the process of being born. Protoplanetary disks. Before ALMA came along, protoplanetary disks were basically theoretical. Astronomers knew they had to exist because planets exist, but nobody had ever actually seen one in detail. Then in 2015, ALMA pointed its array at a young star called Agile Tauri, 1,400 light years away, and captured something that changed everything. The image showed more than 10 concentric rings and gaps carved into a massive disk of dust and gas. Not blurry blobs, not artist renderings, actual structure captured in millimeter wavelength light, showing gaps where infant planets are actively sweeping lanes through the material as they grow. Here's the thing, you're not just looking at some random star system forming, you're looking at a time machine. H.L. Tauri's disk is essentially a snapshot of what our own solar system looked like 4.6 billion years ago. Those gaps being carved right now by baby planets, Almost certainly the same process that built the space between Earth and Mars. The same physics, the same dust, the same slow gravitational ballet that eventually gave us oceans and continents and everything standing on them. But H. Altauri isn't alone. TW Hydrae, only 176 light years away, shows rings, gaps, and spiral structures that look like a planetary nursery caught mid-delivery. These disks range anywhere from 10 astronomical units to over 1,000 astronomical units across. And the dust inside them evolves from microscopic grains into centimeter scale pebbles, and eventually full planets in just 3 to 10 million years. That sounds like a long time until you remember the universe is 13.8 billion years old. This is an eye blink, a window that opens and slams shut before the cosmos even notices. Now, some researchers debate whether every gap definitively proves a planet is present, since dust dynamics alone can sometimes mimic similar structures. But the consensus is clear. The majority of these features are gravitational signatures of worlds being born. No previous generation of astronomers ever saw anything like this. They theorized it, modeled it, argued about it. AIMA turned it into a photograph. But if watching planets form sounds impressive, wait until you see what happens when matter falls into something it can never escape from. Black hole event horizons. Here's the thing about black holes. For over a century, they existed only as math, equations on a chalkboard. Einstein predicted them, physicists debated them, and nobody could prove they were real because, by definition, a black hole swallows everything, including light. You can't photograph something that doesn't let photons escape. But on April 10th, 2019, a team of scientists did exactly that. The Event Horizon Telescope collaboration released the first image ever captured of a black hole's event horizon. The target was M87, a supermassive black hole sitting 55 million light years away in the Virgo galaxy cluster, with a mass of 6.5 billion suns. And the engineering required to pull this off was absolutely insane. The dark shadow at the center of that image measured 42 microarcs seconds across. To put that in perspective, that's the angular resolution you'd need to photograph a golf ball sitting on the surface of the moon from Earth. No single telescope on the planet can achieve that kind of resolution. So the team synchronized 8 radio telescopes spread across 4 continents and turned the entire Earth into one effective dish. The diameter of the telescope was literally the diameter of our planet, but the image itself is where it gets heavy. That bright glowing ring surrounding the shadow isn't just gas. It's matter heated to millions of degrees, spiraling inward at near light speed, emitting the last light those particles will ever produce before crossing the point of no return. You're looking at the final scream of matter before it ceases to exist as we understand it. And the shadow matched Einstein's predictions of general relativity almost exactly. A theory written in 1915 confirmed under the most extreme gravitational conditions in the universe 100 years later. The team earned the 2020 Nobel Prize in Physics for it. Then in May 2022, they did it again. The EHT released an image of Sagittarius A, the supermassive black hole at the center of our own Milky Way, 26,000 light years away, 4.1 million solar masses. M87 was a monster in a distant galaxy. Sagittarius A is ours. Every star you've ever seen in the night sky orbits around it. But if you think bending spacetime is impressive, wait until you see what happens when gravity turns the universe itself into a magnifying glass. Gravitational lensing. The universe has its own telescope, and it's been running for 13 billion years. Here's the thing, when a massive enough object sits between us and a distant light source, its gravity literally bends the light around it, not metaphorically, not in some abstract math on a chalkboard way. Space-time itself warps, and photons follow the curve. Sometimes that bending creates a perfect ring of light. Sometimes it splits a single source into multiple copies. And the most jaw-dropping example has a name, the Einstein cross. QSO 2237 plus 0305 is a single quasar, one object, billions of light years behind an intervening galaxy sitting about 400 million light years from Earth. That galaxy's gravity bends the quasar's light into 4 distinct images arranged in a cross pattern. You're looking at 4 copies of the same object created by nothing but curved spacetime. It's one of the most visually striking confirmations of general relativity ever observed. And it looks like the universe is showing off. But this isn't just a pretty cosmic trick. Strong gravitational lensing can magnify background objects by factors of 2 to over 100. That magnification is exactly how JWST has detected galaxies more than 10 billion light years away. Galaxies that would be completely invisible without a massive foreground cluster bending and boosting their light. JWST has used this technique to spot galaxies that existed less than 100 million years after the Big Bang. Einstein's own geometry, functioning as an instrument extension bolted onto a space telescope. And then there's the subtle version. Weak lensing doesn't produce dramatic crosses or rings. Instead, it creates tiny, statistical distortions across the shapes of billions of galaxies, barely perceptible on an individual level, but when you map those distortions across the sky, a pattern emerges. You're looking at dark matter, the stuff that emits zero light, reflects zero light, but bends it anyway. Weak lensing is one of the primary tools scientists use to trace dark matter's invisible scaffolding across the large-scale structure of the entire universe. So gravity doesn't just hold things together, it reveals things that would otherwise be permanently hidden. But if you want to see what happens when a telescope stares directly into a stellar nursery, the next discovery turned raw cosmic destruction into the most iconic image in astronomy, the Pillars of Creation. You've seen this image. Even if you don't know its name, you've seen it. 3 towering columns of gas and dust, dark and dramatic against a glowing backdrop, looking like the fingers of some cosmic god reaching into the void. Hubble captured it in 1995, and overnight it became the most famous photograph of outer space ever taken. Posters, textbooks, desktop wallpapers, museum exhibits. For an entire generation, the Pillars of Creation didn't just represent the Eagle Nebula, they represented space itself. Each pillar stands roughly 4 light years tall. To put that in perspective, that's nearly the distance from our sun to the nearest star, except here it's just one column of hydrogen gas and dust inside Messier 16, about 6,500 light years from Earth. The scale is absurd, but the image worked because it didn't feel like data. It felt like art, dark, moody, almost gothic. But here's where it gets interesting. In October 2022, James Webb pointed its infrared instruments at the exact same spot, and the result looked like a completely different place. The dark, opaque towers that defined Hubble's version, gone. Webb's infrared light cut straight through the dust, and what it revealed was a nursery. Hundreds of newly forming protostars, glowing bright red and orange, embedded inside the pillars themselves. Stars that were completely invisible to Hubble. They'd been hiding in there the entire time, born inside structures we thought were just dramatic scenery. 2 images, same object, totally different stories depending on the wavelength you use to look. One shows you ancient towers of shadow. The other shows you a cradle full of newborn stars. And the most haunting detail? Those pillars are dying. Radiation and stellar winds from nearby massive stars are slowly eroding them. And within 1 to 3 million years, the pillars will be gone entirely. But the stars forming inside them right now will burn for billions of years after. The nursery will outlive the building it was made in. Something is being destroyed and giving birth at the same time. And somehow, that might be the most honest picture of the universe we've ever taken. But if the pillars show us how observation changes everything, the next discovery proves that the universe itself has been changing in ways nobody predicted. The first deep field image. In December 1995, someone at NASA made a decision that could have ended careers. They pointed the most expensive telescope ever built at absolutely nothing. 10 consecutive days of Hubble's precious observation time, aimed at a tiny patch of sky in Ursa Major that every astronomer agreed was completely empty. The target area was about the size of a grain of sand held at arm's length. A speck. A blank, dark, boring speck of nothing. The image that came back changed everything we thought we knew about the universe. That single grain of sand-sized patch of empty sky contained approximately 3,000 galaxies. Not stars. Galaxies. Each one a system of hundreds of billions of stars, with their own planets, their own physics, their own potential for everything we've ever known to exist. 3,000 entire galaxies hiding in a spot so small, you could cover it with a single grain of sand on your fingertip. But here's where the math gets terrifying. If one tiny speck of blank sky contains 3,000 galaxies, you can extrapolate that across the entire sky. The number you land on is hundreds of billions of galaxies in the observable universe alone. Before the Hubble Deep Field, estimates were dramatically lower. After it, the scale of existence fundamentally broke and had to be reassembled from scratch. And astronomers weren't done looking. The Hubble Deep Field South followed in 1998, confirming the result wasn't a fluke. Then the Ultra Deep Field in 2004 pushed observations out to 11 billion light years, capturing galaxies that formed within the first 700 million years after the Big Bang. Each image went deeper and each one found more. Then in July 2022, JWST obliterated every record. Its first deep field image reached 13.6 billion light years, revealing objects that existed just 130 million years after the Big Bang, with more detail and more distant objects than the entire catalog of Hubble deep fields combined. One telescope, one image, decades of progress surpassed overnight. But knowing how many galaxies exist is one thing. Discovering that they're all racing away from each other and speeding up while doing it is something else entirely. The acceleration of cosmic expansion. In 1998, two completely independent research teams set out to answer the same question: how fast is the universe's expansion slowing down? Because that was the assumption, gravity pulls everything together, so naturally, the expansion triggered by the Big Bang should be gradually hitting the brakes. Both teams used Type 1, a supernovae, stellar explosions with a known consistent peak brightness, as cosmic distance markers to measure expansion at different points in history. They expected confirmation. They got the opposite. Both teams found that the universe isn't slowing down at all. It's speeding up. The expansion is accelerating, and it has been for billions of years. Each team independently spent months rechecking their data because the results seemed flat out impossible. They ran the numbers again and again, looking for errors, instrument problems, anything that could explain it away, but the data held. The only explanation that works is something pushing the universe apart, an unknown repulsive energy filling every cubic centimeter of space. Scientists call it dark energy, and here's where it gets uncomfortable. Dark energy makes up approximately 68% of the total energy content of the universe. Dark matter accounts for another 27%. Ordinary matter, every planet, every star, every galaxy, every atom in your body, every particle humanity has ever observed or interacted with, accounts for roughly 5%. Everything we've ever known is a rounding error in the universe's budget. The discovery earned Saul Perlmutter, Adam Riess, and Brian Schmidt the 2011 Nobel Prize in Physics. But here's the kicker. We've known about dark energy for over 25 years now, and we still have zero idea what it actually is. The leading candidates include a cosmological constant, basically vacuum energy that never changes, a dynamic field called quintessence that evolves over time, or modifications to Einstein's gravity at cosmic scales. None of these has been proven. We can measure dark energy's effects with extraordinary precision. We can calculate that the universe expands at roughly 70 kilometers per second per megaparsec. But the fundamental nature of the force driving 6 to 8% of everything, complete mystery. But if dark energy defines the universe's future, the cosmic microwave background defines its past, and what it reveals is even stranger than you'd expect. The cosmic microwave background. Think of the cosmic microwave background as a baby photograph, not of a person, but of the entire universe. It's the oldest light that exists, released 380,000 years after the Big Bang, the exact moment the cosmos cooled enough for atoms to form and photons to finally travel freely for the first time. Before that moment, the universe was an opaque fog of plasma. After it, light could move. And that light is still moving, filling every square inch of the sky right now. The Planck Space Telescope, which operated from 2009 to 2013, took the sharpest version of that photograph ever captured. And what it found inside that ancient light is honestly staggering. The CMB fills the entire sky at a uniform temperature of 2.725 Kelvin, barely above absolute zero. But Planck's instruments were sensitive enough to measure temperature variations of plus or minus 0.0001 Kelvin across it. That's fluctuations so impossibly tiny that they shouldn't matter. But here's the thing, those fluctuations are everything. They encode the universe's entire composition, its age, its geometry, and its fate. The CMB is basically a Rosetta Stone written in temperature differences smaller than anything you could ever physically feel. From the pattern of those fluctuations alone, Planck determined the universe's age at 13.799 billion years, with an uncertainty of just 21 million years. It calculated the exact proportions of ordinary matter, and dark energy, and it confirmed that the geometry of the universe is flat, not curved, not saddle-shaped, flat, which sounds like a minor detail until you realize it dictates whether the universe expands forever or eventually collapses. But the CMB also contains something called acoustic oscillation patterns, essentially ripples frozen into the light from sound waves that traveled through the early universe before it cooled. Those ripples are where the Hubble tension lives. The expansion rate derived from the CMB sits at roughly 67 kilometers per second per megaparsec, which directly conflicts with locally measured values. That gap might require entirely new physics to resolve, and Planck didn't stop there. It also detected the gravitational fingerprint of dark matter imprinted directly on the CMB, providing completely independent evidence for dark matter's existence through a method that has nothing to do with galaxy rotation curves. Two totally different approaches, same conclusion. All of that from light that's been traveling for 13.8 billion years. But if the CMB is the universe's baby photo, what happened when the universe actually grew up? the first galaxies. The universe is 13.8 billion years old, and in 2022, the James Webb Space Telescope looked back to a point just 220 million years into that entire lifespan. To put that in perspective, if the universe were a single human life, JWST just found a photograph taken 4 days after birth. On July 12, 2022, the very first batch of JWST data revealed candidate galaxies at redshifts so extreme they pushed past anything Hubble had ever seen. We're talking objects formed between 100 and 250 million years after the Big Bang, a period cosmologists call the Cosmic Dawn, when the universe was still clawing its way out of hundreds of millions of years of total darkness. But here's where it gets complicated. One of the most prominent candidates, galaxy GN-Z13, appears to have existed roughly 220 million years after the Big Bang. According to standard models, galaxies at that age should have been tiny, fragile things, barely assembling their first small clusters of stars. GN-Z13 is not that. Several of these early galaxies appear shockingly massive and mature, some containing the equivalent of hundreds of billions of solar masses worth of material, at a point when the universe had barely had time to form anything at all. The model said this shouldn't be possible. And it wasn't just one weird outlier. Throughout 2023 and 2024, multiple early galaxy candidates confirmed the same pattern. Galaxy formation in the early universe operated faster and more efficiently than any current theory predicts. The universe built structures on a timeline we can't explain yet. Now, some candidates at extreme redshifts around Z equals 14 to 17 still await full spectroscopic confirmation. The photometric estimates are strong, but not final. The full picture is literally being written in real time, right now, as you're watching this. And that's not a failure, that's the discovery. JWST didn't just reach the edge of the observable universe. It found something there that breaks our understanding of how everything began. The first light after the longest darkness in cosmic history. And it's brighter, bigger, and earlier than anyone predicted. We're not looking at answers. We're looking at the beginning of entirely new questions, and that might be the greatest discovery of all. If you enjoyed this video and want to see more, click the video on the screen now.